I might have to go.
There was a, because intensity calculation, you're squaring something. And since there was an imaginary component to some of them, I mean, the only logical thing to get the value that we get the value, is absolute square. Yeah, that was 9 pages that I gave to her.
Yeah, 9 pages.
Yeah. I think my midterm was 10.
What midterm? For this?
This midterm.
I think I have like 6 pages. I was working on that finding vector potential A, and then I submitted it, but later I realized there was like a tail question, like, is this unique? And I had not seen that. I had to work on it again.
One, two, three, four. You're losing people. So what's the pattern, Michael? What makes you come here or stay home?
I'm a lab meeting today.
Oh, but Luke seems to be there.
Yes, it's for Physics 101.
Oh, I see. So there are 2 lab meetings that could happen before this.
So you get stuck with more live meetings than most of us.
Exactly.
I'm glad I didn't miss one.
Yeah, I think he was early and Luke is down there. So, and Luke, I have one of your. So you, except yours, I submitted graded everyone else's. You posted some in the extra credit. You posted about that integral that you were struggling with, and I did figure out a way out, but just to write it down, it takes time. So
Right.
I did it on Friday, so I'll send you something, and then I'll grade that.
Okay.
The yours is the only one not graded. Okay. You should go proceed so that. I don't have anything for you, right, Rob? Usually when you give something, I give back.
I don't think we didn't have anything last week.
Okay. And Aliyah is not there. That's not usual. Everyone is logging in. Okay. So we postponed the homework. Oops, what's up? Date today. 21st.
I think that's homework 4.
That's homework 4, yes. And remember, this was postponed, so I'm probably hoping that I'll make this due on September 28th. It's tentative, so keep it watching.
You will push
And midterm 1 is over today. And midterm 2. So Monday. By default, it's in class, so be prepared for it, but it might change. Like I'll at least give you a few days warning if it is not in class. We were trying to derive the conservation of linear momentum. Linear electromagnetic momentum. And we started with the force equation. That was our guiding principle. So linear momentum means rate of change of momentum is a force. So that's why you start with the force equation. That's the idea. And this is the idea of moving charge with the velocity, and that's the charge itself. And you immediately divide it by volume and interpret this whole thing as a local definition. And the top one is also local in the sense it is on a single charge. Now it's on at each volume element in it. Okay. Let me not write the dependence in the next term. That's G cross D. We used Maxwell's equation to replace the rho and a J. And what rho, I know. It is del dotted with E. And J was del cross with H minus of d by dt E cross with E. And this time derivative stops on D, like it doesn't act on. Like typically, the notation I use is that if you keep the derivative open, that means it's acting on everything on the right hand side. So if that's not the case, then I try to close. Yes.
Lorentz force is the, but what is the name of the low F force? What do you call that?
There is no, this is also Lorentz force, but you can say this is force density. Right? That's the, but it's also Lorentz, it is the Lorentz force, but interpreted for a charge distribution. That's the way to see. Helps?
Yeah.
And I would call it force density, but check out. I mean, may not be very common to use that.
Yeah, so
it tends to call it force density. Yeah.
Just in this course so far, when I'm trying to do like outside, so after I read through the notes again and try to find resources to help, like looking for names of things to search for, because if you just type in conservation of linear electromagnetic momentum, there's a million things that pop up that
what I suggest is start with chapter 3 of our assigned textbook. There should be I pretty much follow that. I mean, if you look at it, at least at this stage, so that's the lucky part, I don't follow it all through, and I don't follow it one-to-one, like page to page. But at least chapter 3, I think you will see that it's broadly exactly the same. I have heard the comment once that, so this was unofficially, I heard it from a third person. I take it as a compliment, but it is not really. So the undergraduate student who was close to me, he said, it's not only the content that matches, it's the font also that matches. So that's kind of it. So I would say look into the book. You might be surprised that, especially since you guys have taken classical mechanics with me, and I agree that I don't follow standard textbooks, so content doesn't follow a specific book, but this case is slightly different. It is, you'll be surprised that it is a lot similar. Yeah, so I would say give it a shot, and again come to me otherwise. I've heard this comment before, and what I've done is that in homework I've given keywords to search for, because I know people go and search in the internet and given keywords. But I think in this case, textbook is the place to go, I would say. Textbook means Stringer's, Stringer, Milton, Dirard, and what's the last one?
Okay.
Sai, right? I don't know how to pronounce that. Okay, so okay, so that's your equation, but then we added some zeros to it, right? So it is a 0 because magnetic monopole doesn't exist. So this is del dotted with B times H, right? Because this is 0, I can always add that to it. And the second equation, I think we agreed that this will be a negative. So this is negative and del minus del cross E and plus dB by dt, again cross with B gets to D. Yeah. So each of this is 0, but it's because magnetic monopoles. In fact, based on this, you can actually write what will be the Lorentz force on a magnetic monopole, right? That's one thing. If there was a magnetic monopole, what will be the force? Or you don't have to really think of magnetic monopole as a separate entity. You can also think of a particle that has both an electric charge and a magnetic charge. Right? That's also that it doesn't have to be a separate property altogether. Then the force on that such a particle will be this is charge density, electric charge density, magnetic charge density plus rho m times h. And this is, notice, minus. So this is minus of Jm crossed with D. So one should be able to motivate that. I mean, that since we don't have any intuition for magnetic monopoles, that's not straightforward, probably. But that's one way of starting. You can say that that is there, and then you reach here. But I'm trying to put in zeros. I'm trying to do that. And I think in the textbook they do put that third extra terms and then introduce the monopole.
So what is the motivation? Like since it's not a tested quantity and it's never been
Set it to 0 at the end. It is not a tested quantity. That's why you set it to 0 at the end. It's just a mathematical trick, if you want. Right?
Yeah.
Or the way I'm doing it is that this is 0, that's 0. I can always add zeros. Correct? So, or you can say that if you want a feel for the 0, introduce something and set it to 0 at the end. Like you will get a charge electromagnetic momentum, which is having both contributions from the charge and the magnetic charge, but set that to 0 and you're in your normal world.
okay.
Right? So, and since there is a lot of bias among people that, yeah, it must be there, and mainly because of the equations, it seems like, oh, there's a lot of symmetry in there. There might be a good chance that it's there. So because of that, they explore that. Okay.
I have
So,
one question. So
yes, please.
the second term in Faraday's law, should it not be minus?
Oh, yeah. No, right? Yeah, both, yeah, because this is negative, right? Yeah, sorry. Oh, then did I mess up? No, I did not, because there's a cross product outside this one. Okay. Yeah. Yeah, I forget this cross product. I count it for the cross product. Last time I said plus and then switched to negative later. Okay, so that immediately lets us write, and this is where we were last time, I think. We saw that the time derivative distribution can be collected together and written as minus time derivative of d cross d when it distributes itself. There are two terms in this. First one is with d, that's this. Second term is with b, that's that. And remember, our goal is to write it like a continuity equation, time derivative of something and the divergence of something. So let's say that, yeah, so let me just write it as such here. So this, for now, I simply code this. So this is d times e, and this is plus cross e cross with d, and there's one more term here. And our goal is to write this as time derivative of something. So let me write this as, I can define this to be the momentum density plus, I want to ask, is it possible to write this? Is these two, like there are four terms in here, right, which has a gradient. Is it possible to write it as a divergence? It's not obvious at all. And the force. Yeah. So, like this is how your textbook puts it. Like it will say, if it takes a question mark, can we write this in this form? Or maybe it's not in chapter 3 they give us it. This is again revisited and when you bring in the materials, and currently we are all in vacuum. So what is G? G is simply D cross B. And the question we are asking is, can we write T, right, is this equal to? So let me rewrite this with a slight difference. Let me write this as D cross. The back cab rule is valid for A cross, the associativities. And remember, we are in classical electrodynamics. There's no quantum features, so E and D kind of goes through each other. And there's one more piece in here, plus. Even otherwise, this actually goes through because in vacuum, D is epsilon naught times E. Right? Remember your definition. E is epsilon naught times E. If it is a material, there is a dependence in there. This is minus let's start with the top one. These two are pretty much identical if you replace B and D, right? So we have to work with only one piece. So let's do D cross with cross E. That's your, if you want to use back cap, but you want to be careful, right? So in the backup, this is your vector, free vector in the first term, but then it has to act on the on the E. So the way I would, I can write this is that this is D. How about this? J L E. This means that this is dotted, and I'll rewrite it, which is in a better form. And plus, this is the free one. So this is D dotted with L of E. Remember, derivative acts on everything on the right hand side. If it's not acting on everything, I have to use brackets to clarify that. So this acts on this. I can close the brackets in there, but then I can move the D back in there. So this is del of E. And now notice the dot product is with D. This clarifies that derivative acts only on this, but whatever is a vector on the right hand side is having a dot product with this. So hopefully with the bit of vector calculus or the index notation and dyadic notation, this is not very bad. Okay. And did I capture everything? We also have one more term in here, right? If we want to get that last piece also, let me introduce that. E minus E
So T is a stress tensor. Is that what that is? Like what is that?
E.
T?
It is going to be the stress tensor. As of now, yes. Answer is yes. Yeah. But I haven't yet used the word, right? So yeah, I'll define it as a stress tensor. But the way we have been telling it, the best way to look at it is that it is a flux of momentum. Right? A flux of momentum density. It's like the pointing vector is the flux of energy. When you think of energy, there is only one direction. So give me a direction and you ask how much energy is going in that direction. But when I say momentum, there is a lot of things, because given a direction, I can ask about how much X component of the momentum is going, how much Y component of the momentum is going, how much Z component of the momentum is going. So in that sense, it's a tensor. So I would say flux tensor is a nice word, but yeah, the popular word, the key word to use is the stress tensor. Okay. Yeah. And put this again in here. So this is with T, and put this. I introduce this first, and I'll write this term. Little squeezed out there, but again, if you notice, this term is again a distribution. If I were to think of this as D times E as a factor, the first hits this or hits that, with the dot product always with D. Right? So there's a derivative that is distributing, but the dot product is always with D. And also notice the first term, let me first do the first term here, dotted with D. D is nothing but epsilon naught, so that's epsilon naught. Electric field is symmetric. Notice that I can make this a half, and again write this as how do I write this? Maybe it's not transparent. One second. So this is minus epsilon naught of half the point is this is symmetric in E, whether I take the derivative on this first component of or the first electric field or the second electric field that comes as a dot product, it doesn't matter. So this is exactly the same. If you and that is the same as half of E dotted with D. Any questions on that? So that's equal to.
Yeah, where's the half come from again? Just.
Notice here in the first line, the gradient acts only on one electric field E,
Mhm.
and the second one is outside the bracket. That means that the gradient doesn't act on that. Now, in the second expression, I say that no, I'm going to let it act on both. So it acts on this and that, but the second one is exactly the same.
Okay, I
Right?
got you.
Because E and E is, I can move it around, it's all fine, it's exactly the same, so I have to put a half in there. And the goal is that notice that this is an term that appears in the energy, right? So that it seems like this is related to energy. So this is minus. Actually, I should be careful, right? This is minus of del dot T, right? Because I put the T on the left-hand side, and these are all on the right-hand side, so I want to define this as negative of that. Right. That's just it. So this is half of E dotted with D. And this here, as I said earlier, is a distribution property. But this is now a tensor. And again, I can write E dotted with D or D dotted with E. Let me write this here. But I can move the epsilon naught from here to there and write it as E and D. Doesn't matter. Okay. And I messed up again. Hold on. Yeah, it's okay. I want to collect these two together, but this is a free vector and that's not a free vector. So how do I do that? Right? If I want to write this as negative dotted with, I would like to do this. And this is clear that this is plus D times E. What about the first term? Is that okay? Can I write that as a dot?
Yeah, I think so.
No, right? That's not okay because this is a scalar. How can I dot it with a scalar?
Well, I thought you were asking if you could dot the del, which you did.
Yeah, but this is dotting with what? Like this is nothing, correct? This is not a vector.
Yeah.
But the second term is a dyadic, so that gives a hint that second term is a dyadic, first one is also has to be dyadic. So you introduce a 1 there. And if I want to interpret this as a dot product, I want to introduce a 1 there. It's like saying I'm thinking of a matrix, but it is not a matrix, so that means there is an identity matrix sitting there. Right. So this is a dyadic, or this can be thought of as a dyadic. So that's a 1. So that's the 1 that I introduced in.
I have one question.
Yes, please.
So in your second last equation, you have plus and minus in two terms, but
Oh, what happened to that? So that's a mistake. And remember that that is exactly the same thing for B's, right? So, and since there is an overall negative sign, I recognize my flux of electromagnetic momentum density to be 1 times half of E divided with D plus half of H divided with D minus of, I'll move the epsilon naught from this term to that term, so I can write this so that there is symmetry in there. It's D plus H times B. That's your electromagnetic, or the flux of the electromagnetic, linear electromagnetic momentum, if you want. If you notice, this is nothing but the energy density, electromagnetic energy density. So I can immediately say this is 1 times U minus of E where, remember, my energy density is half of E divided with D plus half of H divided with B. Recall, I mean, I'm writing it in a slightly different way in a vector form. You should all just make it very visual. This is nothing but this, right, which we are very familiar with, or should be very familiar with. Not. So this is like often in undergraduate course, you will say, if you want to see how much energy is stored in the form of electric field in a capacitor, that's what you will cover. That's the first time, I think, at least these days, it's so much standardized courses, so that's where you start seeing it. And this is how much energy is stored in a solenoid, right? So it's a solenoid that is magnetic field, and how much energy is stored in that. It depends on the volume of the solenoid. So it's just a way of writing it in the form of vectors so that you can see the dyadic structure more clearly. So appreciate that. And if you want, there's also S, right? The flux of energy density, which is the pointing vector, is E crossed with H. And you see that this is epsilon naught, mu naught times S. And epsilon naught mu naught is 1 over c squared, speed of light showed me. So this is momentum, that's energy. Momentum and energy are off by a velocity usually, and here this is the velocity of light showing up. So this is a clear signature. So right when Maxwell wrote it down, so this is the first things you do. You play around with the equations, and it seems like, oh, there is a something having the dimensions of a speed showing up. Okay. Any questions at this stage? Right. So this is our equation if you want. So, and we would like to use it, right? So this is as such, Maxwell's equation is already, I mean, if you're not very familiar with it, if you have not taken undergraduate courses, it's not the most straightforward equations. That's a lot of coupled set of equations. And this is a derived equation out of that. So except for the fact that we have a field for continuity equation, and that rate of change of momentum is force. Otherwise, we don't have much field for that. So let's try to do an example, as a relatively straightforward example, and see how you would use this machinery, right? And yeah, okay. Any questions or comments?
I guess I have one
Yes.
question. So when we calculated the divergence, the term inside of the divergence, we have a tensor product of dE. But in the next step, we write ED. Is it because D and E are essentially the same?
Yeah, because it's essentially, I moved the epsilon naught from here to there. If you don't like it, write it in this form. This is crucial in the way that currently it is vacuum. This needs to be extended for materials, right? And I should say that it is still controversial how you do that for materials. So it's 100 and now it's how many? Yeah, it's probably 120-year-old controversy. It's called, we need extra credit, right? Yeah, extra credit problem. So extra credit problem is, this is Abraham Minkowski. You can say controversy or, yeah, let's say controversy, okay? Controversy on electromagnetic momentum. Okay, pretty much spoiled that, but I guess that's okay. But don't confuse with what we have done today. Whatever we have done today is there's no issues there. But when you make this to a material, then there is a challenge. Basically this momentum, the question is this the momentum? Is this you divide it by a speed of light and say that it is E crossed H with the speed of light. So just it's a speed of light, that's an issue. And then one would think 120-year-old controversy, and this turns out to be one of the most precisely tested subject also. One would think that experiments would settle that, especially if that is just an expression that's in there. Because it's a time derivative here, and usually these are optic experiments, and optics, remember, involves oscillations of 10 raised to 15 per second. If you convert your wavelength into frequency, that's a huge oscillations, and or the frequency is extremely high, and it's the best way I can say is that it has not been settled yet. It is also a lot of bias there that no one wants to. So typical science debates which is still going on, and we don't have an answer yet. And in this case, I think there is no such thing as there's a major part of the community believes in that. That's also not the case. So this is still really, as far as to my knowledge, open. So that's something, you guys as young people, you guys want something to work on. So those are things that you can settle, right, with the non-trivial answers. Okay. So let's use this equation and try to do something. So, G of T plus F is equal to 0. So let's apply this to a very simple system. That is a charged sphere sitting there, uniformly charged sphere. And we know that it's uniformly charged sphere. That's one thing. And the question we could ask is, right, the question is, if there is a charged sphere, all these charges are trying to repel each other, right? and we could ask what is the stress on it. What is the stress has to do with the force also, right? But we don't talk about the force, let's talk about the force per unit area. Like what's the force per unit area on the sphere. And caution that there is no other charge here. Right? So it is not that we are talking about another charge and what is the force on it. This is the, if you want the self force, so which is a very, very tricky topic, right? It's almost like saying that you're sitting on the chair and you're saying, can I lift the chair? So something like that. It's a self energy, if you want to hinting on it. And that's your electric field for sure.
Is it force per area on the surface alone, or is it?
On the surface, yeah, on the surface, yeah, let's say pressure on the surface, right? That's what, I'll define it a little more precisely later on as we go. Okay. And this is charge Q inside in there. What else can I give? Yeah. So since it's a charged sphere, I know the electric field for sure. So I know the electric field as a function of time also. It's static, sitting at the origin, let's say. So that's electric field is 1 over 4 pi epsilon naught, and sitting at the origin, it is r hat over r square. Is that what it is? Any clarification?
Times the charge.
Huh?
Times the charge.
Oh, times the charge, yes, sure. That's not intentional. Something more you want to add? What if I'm here? Then the electric field. So let's say this is r greater than. So there is a radius of the sphere also comes in, right? So that's radius r. So this is for r, for capital R less than r. Let's stick to that. I mean, remember that if what is the electric field inside, by the way? Like, I'm not going to use this today, but what is the electric field inside? Anyone? Oh, no, not zero, right?
I think it has.
Because it's not zero because you can think of it like this, right? Inside is another sphere, right? So electric field here will be controlled by that. And the electric field from the shell is usually zero. So it's the electric field of this that contributes, but then the charge is less. So you have to compensate with the distance and the charge. And it turns out that it is linearly increasing. So it is R over RQ. Did we talk about this Rutherford scattering and all? No. Yeah, it's a good discussion, but I will not go there. Yeah. Extra credit. Yeah. Yeah. How is extra credit? I think do this for yourself. I feel it's how did Rutherford, remember that historically before 1910, we did not know that electrons were actually going around the proton in circles. We just thought there are electrons and protons inside the atom, that's it. And they were just sitting there to be, it was very convenient to put it in there. And so the point is, how did Rutherford deduce the atomic model? like try to get the logic there, that it's very important, I would say. And if you really want to take a leap there, you can ask, can you use this or similar logic to deduce something about, okay, it's a big word, dark matter. Okay. Now, don't ask me what is dark matter, that's also abstracted. So my point is that whatever Rutherford was facing at that time, that he had an experiment and the atomic model was not matching with that. Similarly, we have a situation as of today that we have an experiment saying what are the velocity of stars inside a galaxy, and they don't work with the theory. Like simple Newton's law fails them. Like we have all studied Newton's law. Half mv square is equal to half mv square is equal to g m1 m2 over r square, right? So something going m2 m1. If you use this in our galaxies, for that matter, any galaxy, and plot velocity with respect to radius, there is a huge discrepancy, a huge. It's not just one person, and a huge discrepancy, and whatever is missing is what we call dark matter. And that immediately says that, oh, we're missing something, and that is exactly what Rutherford had. His experiments were not matching, and he did something to fix that. So why are people not fixing it for the dark matter? Why don't change the model of galaxy? And it turns out that they've tried that, but that's what we have an explanation for dark matter. Simple explanation for dark matter is that, but still it's not sufficient. So do that. I think it's a nice thing to be aware of. And remember that the moment you say it's a planetary model, that came up with new challenges. What is the new challenge one had with the planetary model of atomic model? What is the challenge we have as of now? Atomic model.
Discrete orbits you're talking about?
Yeah, discrete orbits. And I think the point you want to make is that the moment it is going in a circle, that is. Cover again?
It's a lose energy and electrons
Yes.
collapse to the nucleus.
Exactly. So the point is, if there is a charge that is moving around a proton, it is accelerating by definition. If something is going in a circle. And there is an independent relation in electrodynamics again, that if a charge is accelerating, it has to radiate. So it will lose energy. If it loses energy, and if you calculate that, it's in nanoseconds, your electron should collapse into the proton. But our hydrogen atoms are very stable. So that's a new challenge that comes up, and quantum mechanics is a big attempt to avoid that, keep our hydrogen atoms stable, if you want. So it's a kind of nice little history that this is all 1910. So 1910 is when Rutherford did that experiment. So before that, we didn't know that our atomic model was like that. Not very far again. Yeah. Okay. So that's. And again, I think I won't need this information for less than. Okay. So that's your electric field, and what's the magnetic field? For a charged sphere, there is no time dependence. You notice that T is just not there. What is the magnetic field? Right. For this? Any doubts? Yeah, it's 0. Yeah. So it is 0. So we immediately know that your G is 0. Right? So G is 0, right? Magnetic field is 0. And we can ask what is T now. So, and we actually now want to use this equation somewhere. So let us say we want to integrate this. Right? So we are interested in finding the stress. So let's have a small, tiny abstract sphere enclosing this charged sphere, and make it relatively close enough so that we have that we can recognize it as a force exerted on the sphere itself. So this whole thing is an enclosed surface, so that the continuity equation works. Then, right? So when you integrate that equation, this becomes d by dt of integral of d cube r of v of g plus d cube r. Or actually, I don't want to do that. Give me a second, sorry. Let me first, since there was a question about what do you mean by force per unit area, right? So let me not integrate this equation. If this equation is correct, I can always take the dot product of this also. So this is, let me take the dot product with respect to r hat. Plus. Notice that the free vector for this is on the right hand side, so I have to take the r hat on the left, right hand side, right? So there are two vectors, there's one vector, one of the component is taking the divergence, so dotted with r hat. The gradient acts only on the stress tensor, plus r dotted, r hat dotted with f, doesn't matter left or right, so I think I do this. This has the interpretation that this is the radial component of the force. And again, we already said G is 0, that's equal to 0. And now, after taking the component, let me now integrate this on the sphere that we are talking about. So that's 0 anyway. So this is 0 plus. Plus Q R F R hat. This is on the volume V we are talking about. There V is this is your volume V, right? And close it up. This will interpret as, since it's a radial force, this is a total radial force. Right? So this is a total radial force. This is a scalar quantity. It's a component of the force you're adding. So if you divide it by that area, then you can think of it as a pressure. So this is the total radial net. Net radial component of force, which is what we need for the pressure. Okay. Why am I struggling at this point? Um, Let me just explicitly do it. Yeah. I was wanting to use divergence theorem, but I'm a little hesitant to do that because this dot came up, right? Which I think is harmless, but let me not get in there. So instead, let's do this as a volume integral. That should give you the same answer, I suppose. Yeah, sure, because it's a mathematical identity. So del dotted with t. So first, let's write t, right? T is equal to 1 times half of E dotted with D, which is nothing but epsilon naught E dotted with E, right? And there is no magnetic field, so that's 0 minus of E and E again, right, with the epsilon naught. Substitute your electric field in there. So this is equal to 1 epsilon naught over 2, and then we have q over 4 pi epsilon naught square. And let's do this for so we will evaluate this for r equal to capital R plus a tiny delta. So this is greater than 0. Slightly. So this is on the surface that we are talking about. So this is r hat over r square. No, but I want to integrate it. So after all, I did want this, I guess. Yeah, usually I do it on the surface, and yeah, struggling here. Yeah, so let's do this inside the sphere. Right? So we need the inside part. Sorry, so this is r over r cubed squared, and then there is r hat dot with r hat. Right, let's give square at this minus of epsilon naught. And again, pretty much the same thing, except that 2 is not there. Q over 4 pi epsilon naught square and r over r cube square. And this time it is r hat. R hat, these are free vectors. And all this is for r less than r. So maybe the first statement I should remove. Inside the, I'm going all the way to the radius. So, okay, this is okay. So this is equal to 1 of the epsilon cancels. So let's rewrite this. So if I 1 by 2 q. So this is q square over 16 pi square times epsilon naught, and r square over r raised to 6. R dotted with r is 1. And this is 1 by 2 times 1 minus of r hat. Take this. So that's your del t actually. but we want to take the divergence of this and take r hat. And when I take the divergence, I like to do it with r hat down. So let's do divergence of, yeah, let's do divergence of t. So there's an r here, two r's are there. That's fine. Maybe I want to rewrite it slightly again. So q square over 16 pi square epsilon naught 1 over r6 is constant. And we have 1 by 2 times r square. And this is minus vector r, vector r. Okay, because r squared is that's here. When I put it there, I make that a vector r into r hat. And remember, we know these identities that gradient of the vector r is just 1. And great, well, this is the outer product, right? And the gradient of the magnitude of r is just r hat. That will help us do the divergence of the stress tensor. So this is all a constant, stays inside 16 pi square epsilon naught 1 over r raised to 6. Divergence in here, so this is the same as 1 by 2. The 1 can go with the divergence, so this is supposed to be a vector, so that's r squared. And minus of I can hit this one or that one. So you have but the other one is exactly the same. So there's 2 times that. Okay, it's correct. Open. Work on this, use this relation. It's q square over 16 pi square epsilon naught 1 over r raised to 6. 1 by 2, this is 2 times r. The differentiation, then you have to take the gradient of r, that gives you an r hat. Differentiate this chain rule, r hat. This is a unit dyadic, but then you have to take the trace of that, or the divergence of that. That gives you 3, if you remember from your first homework. So this gives you, if I had to put a dot in there, or the divergence in here, this becomes a trace. That's your 3. Right? Is that familiar? So that's your minus 6 or 6 times vector r hat 5. Really? We'll see. So that gives you q square over 16 pi square epsilon naught 1 over r raised to 6. And this is a minus. This is 1. That's at 6 minus 1. That's 5 times vector r. Take a dot product with this, and we should be fine. And then we have to integrate that perspective. Right, so that's our hat equal to This is when I do that, so that's 5 times 12. I think so. Okay. We have to integrate this over the volume. So if we want to interpret what we have on the left hand side, so I do the integral. Is this visible on the camera? Still have room, right? So d cube r there is no angular integral there, so that's 4 pi. And I have 0. Notice this volume is going all the way to the radius r, right? Radius r, and that is r square r. Right? That's a volume integral. If you want angular integral, gives you a 4 pi, and we put the negative sign outside. Q square over 16 pi square epsilon naught 1 over r raised to 6, and that is 5 r. And that is equal to minus. So one of the 4 pi's cancel out, so I surely have a q square over 4 pi epsilon naught. Q square 4 pi epsilon naught, and then r cube integral gives me a 5 r raised to 4 over 4. 5 r raised to 4 over 4, which is r raised to 4, so this is 5 over 4 r squared. Right? So that is 4 r's coming in the numerator, cancels out 4 of them, so there's only 2 remaining, and the integral gives you 4. So, so let's interpret what this is. This was your total force. Let me call that FR. Yes.
So there we considered, we said that we wanted to integrate along a sphere of radius slightly greater than r.
Yes. Very slightly. So basically everything is inside.
But there we went from 0 to r.
Yes, so you make it r plus delta if you want. But that won't change anything because the delta is higher order. Right. When I was writing that down, I was hoping to do the surface integral there. That's usually what I do, and that's much more convenient. But then something stops me from doing that here. So I went the completely different path this time, and hopefully they get that. I mean, we have an answer there, but I'm not completely satisfied. So I'll come to that discussion later. Okay, so that's your. Oh yes, did I miss something? If you find an error, let me know.
I was just wondering, whenever you took the divergence and the identity one and the line above that, where did that go?
Oh, so this is so that is what we have here is del of dotted with 1, right? And then there is r squared. If you want, it's like that, right? Del dotted with 1 is del itself. I think of it like del dotted with 1 is del j I index house, and this will immediately make this del I. Any other questions on the slightly different math? Here doing like the dyadic features. Okay, but now comes the interpretation time. This is the force radial sum of all the radial forces. is equal to negative of this whole thing, correct? On the right hand side, but the negative of this whole thing will be just remove that negative sign. So this is q, so 1 over 4 pi epsilon naught q square over r square. So it has the dimensions of the force, right? So there's a factor of 5/4 there. Extra piece in there. If you want to interpret this as a pressure, which is often more convenient if you want, so you would say pressure would be f of r divided by 4 pi r square. So then you would say this is 1 over 4 pi epsilon naught, and this is q square over 4 pi r raised to 4 times pi over 4. And now I say that, yeah, we should get this. But I think the phi shouldn't appear for that. Seems like it was there.
I don't know if I remember correctly this or not. I mean, we did this 7 months ago. I think we had like 2 R hat, so we were giving something.
Yeah, but I was doing on the surface. Like I typically do it on the surface, and this is it. That's much cleaner, easier integral actually. Because then you don't do the integral, it's pretty much practically immediate there. But I don't see the error there. Yeah. Why is this course always I'm messing up? Yeah. So as of now, so I'll just sit like this. I'll come and fix. So here there is an error. Okay. So I'm gonna think about it. Okay. I don't think it's for me. It's not for you guys. Like I'll think about why that's a file. Yeah. I don't see that as of now. It seems to be off thing. I'll confuse you guys completely in this course. First there was the delta functions, so now there's okay. That's all. I don't have anything else. Maybe I should add on to that this is interpreted as the pressure on the sphere, right? That's the point we're trying to cover, stress on the sphere. And historically, maybe I should add that this played a big role. Like remember, before Einstein, you might have heard that there is this idea of ether, and so this is a structure of ether in the sense that the claim or the idea was that the inertia that a mass experiences, like mass is associated with inertia. That means to say that if I am moving, if a heavier mass is moving, I have a bigger tendency to get pulled backward. So the idea was that this radiation field that's there with it, it is moving with it, and that's what is causing the inertia. Like these lines, so if it has to move, it has to build the whole lines with it, and that's what is causing the inertia. That was a big project Lawrence and Poincaré and everyone had in their mind. And until Einstein came and he changed everything. He said, "Oh, this is." So he just changed the interpretation. Actually, the whole algebra stays the same, but then he changed the interpretation, except this part, and this just falls off after that. This is how they tried to do that, and this just came apart completely. and people started working in this form, like field concept was sort of took a setback in that, if you like. Yeah. It's called the electron model. Yeah, you wanted keywords, right? So this is called electron model. It's considered a failed model. Right? Electron model, look up if you want. Lawrence is associated with it. Lawrence, Abraham, Poincaré, Abraham, Poincaré. It's called Poincaré stress. Like the stress that we're talking about is called the Poincaré stress. Sort of very nice to see the ideas that go through in there, but remember that it's a wrong model, it's a failed model. So failed in the sense, obviously they couldn't deal with it, so there were a lot of inconsistencies inside the model. You do it one method, you get something, you get another method, you get something, and yeah, and my own issues today. That's a different thing. I don't mean that. So that's all. Thank you. I'll try to get that fixed. Questions? Comments? How did the midterm go? You still have time to submit, I suppose, if you're not submitted. I think I realized it was due at 11 p.m. apparently. Either it was my mistake or I intentionally did. I don't remember.
I think we need to do 11 a.m. and then.
Probably. Yeah.
I had trouble following the logic on the fifth problem, but
Today's thing? This one?
no, on the fifth problem on the exam,
Oh, on the exam. I see. Okay.
I struggled following the logic, so I just
So you just wrapped it up. Is that what you gave up, or?
basically
Yeah.
first.
We still have office hours, one more office hours, right? So you can ask maybe if you have, if it is something that I can answer without revealing the answer, I will be glad to answer. Yeah.
It's kind of one of those
Yeah.
problems where I feel like if you answered my question, I would be able to do it. I feel, but it's just not that big a deal.
Did everyone struggle? No, probably not.
I don't know that I got 5 completely either.
I was the troubled one.
Okay, so how about this? Is everyone available at 3 o'clock today? 3:30, let's say.
I'm
3:30.
not, but if you record it, I could watch it.
Record it. Office hours recording. Okay. We'll record the office hours. Yeah. Okay. So yeah. So if you cannot come, I will. Where do I post my office hours recording? Yeah, we'll put it in the playlist that is there. Yeah. Okay. So I can go over that.
The first, A, B, and C were pretty straightforward, but then there were some leaps that I guess I didn't understand, and
Here is it before problem, before 3 o'clock. Problem 4 in the home or in your exam is what you use to do problem 5.
yeah, I got
So
that.
that's a hint. So it should be, if you're done problem 4, it's exactly what you use in problem 5 in some form or the other. But anyway, so let's do it at 3:30, and those who cannot attend, you can watch it on the later on. So you will have very few hours after that, right? 4 to 11. But then this is an exam. It was supposed to be 1 hour. No, this exam is not 1 hour. If you exclude the problem 5, it is 1 hour. Yeah, that's all. Yeah. Okay, reasonable.
Yes.
Okay, good. Okay. And I said 3:30 because 3 o'clock there is a student who might come up from other class, so that's why I said 3:30. But we can extend it a little further if necessary. Okay.
Thank you.
Yeah. Goodbye.
Thank you.
Mhm.